Overview of computers and programming. Are we going to spend a lot of time in this chapter? No, because we already know what hardware is. It's the part you can touch. We already know what software is. It's the part you can't touch. In other words, the programs that we write. So what is a computer system? A combination of all the components required to process and store data using a computer. What's a computer? A computer is a programmable device that follows a series of instructions. That's all it is. You can create a mechanical computer. Yes, sir?
You start recording.
Did I?
You hit the record button.
You're my hero. Thank you for asking. Thank you for asking. All right, so it's just a device that can run a series of instructions. You can write a mechanical computer with gears. Did I show you this already, what a Pascal computer looked like? Not a Pascal computer language. That was just named after Mr. Pascal. Yeah, just like that, right? Early 1800s, numbers were exploding. You know, the British Empire wanted to be able to track all the gold they collected, and trading routes and astronomical positions and stuff like that. And doing math is hard. So what you would do is you would have great big books full of tables. And if you needed to know what the logarithm of 8,371, you'd go to the library, you'd check out the great big book of tables, and you'd look up that logarithm, because there's no way to calculate it on the fly. Well, yeah, you can calculate it on the fly, but it's very tedious, and you wouldn't want to have to do that. So to make these kind of tables, or if you're just sitting there trying to balance your books, a couple of guys, the first one to do it was named Blaise Pascal, made what's essentially a pocket calculator. You set all the dials, and then you turn some kind of crank. Maybe that's the crank, not sure. And you set the dials again, and one of these is going to be an operator, like an addition or a multiplication or whatever. And you turn the crank again, and then all of the numbers up there give you your answer. So that's a calculator. Not really a computer, though. Why is it not a computer? I mean, it computes things, doesn't it? It doesn't follow instructions, right? It doesn't have a series of operations you can do. You can't tell it, okay, the first thing I want you to do is to add those two numbers together and then take that result and add it to another number, right? There's no way to give it a program. It's too simple for that. But, lo and behold, a guy named Charles Babbage did invent a computer in the 1800s, an honest-to-goodness computer. Part of it was the data. Part of it was what was known as the information store. I think they had a different name for it, but just like the RAM in our computer. And then part of it would store the program. Well, it didn't store the program, but you gave it a punch card to have your program in it. Well, that's crazy. How could there be punch cards in the 1800s? Because the textile factories already used, let's see if we can find one. Devices for creating cool patterns in your fabric, because people would pay more for a blanket if it had a cool pattern in it, right? And so they were run by punch cards to create the pattern. Primitive punch cards, right? But heck, that's pretty cool, right? So you could program, in effect, that textile machine so that it would use the different patterns of thread while weaving the cloth based on what was in there. So he took the same idea and made it so that you could use that kind of punch card to give, and where'd it go? Numbers to feed to this thing, to put them in the store, the information store, and then you could give another series of punch cards which would tell it in what order to do math on it, right? To add these numbers together and use that result to add against the third number, that kind of thing. So that was an honest-to-goodness computer. Did he get it working? No, because this involves an incredible amount of precision brass instrumenteering, right? You had to have tools incredibly precise just to make the gears and the stuff like that work perfectly. And so it took a long time to build, and he got his funding yanked, right? It was pretty much beyond the capacity of doing it. But people have made them now. People have made them, like if you go to the IBM lobby in Rochester or something like that, I made up the position, the name of that location off the top of my head. But anyways, you can go into some museums and you see a mechanical computer like that. Now that would be the actual first computer. And so there was an entire genre of science fiction, I know you've heard of it, called steampunk. Because a couple of guys wrote a book called The Difference Engine. Why is it called a difference engine? Because one of the things it was good at was taking the differences between a series of numbers. But anyways, and in that science fiction book, computers had been invented in the 1800s, right? And so technology had, advanced a lot more, and you had steamships, and it had all sorts of computers. Anyways, that's where cyberpunk came from, is the idea that that thing was invented and actually worked. All right, that's about enough of that, but I think that's more fun than this slide. So what is software? Software are the instructions that tell the hardware what to do. It's written by humans, for the most part. Yeah, you could have a computer writing software. That's kind of a scary thought. And then what are programs? Programs are a series of logical commands written in whatever syntax that particular language uses. And there's hundreds upon hundreds of programming languages. Some of them are invented just for fun. Others are invented because somebody looked at all the computer languages they wanted to look at and said, well, it doesn't work the way that I want it to, so they make another one. Right. So what is application software? Those are your games, your spreadsheet, your word processing, your stuff like that. And what is system software? Well, that's the operating system, right? Like Windows or Linux or whatever. And then the utilities on your operating system, like for formatting your hard drive or setting your card settings or stuff like that. So computers generally do three things. They do input, they do processing, and they do output. That Pascal calculator did input, processing, and output because you turned the dials, that was your input. You turned the crank to make it do the mathematical operation, and then the little numbers appeared up at the top. That was the output. So the syntax are just the rules that govern the way the language is put together. Just like in English, we tend to put the adjective in front of the noun, right? We say the green tractor. In French and in Spanish, it's vice versa. The noun comes first and then the descriptive term comes after it. So I don't know the French terms for green tractor, but the tractor green. Yeah, so it's just in a reverse syntax. And and in some languages you put the question mark in front of the question as well as at the end. Right, that's a difference in syntax. And if you're going to write the proper questions, in written form, then you better have that upside down question mark. So in our language, we have a syntax where some things have a colon at the end, and those things that have a colon at the end are followed by one or more lines that are indented. I think we've done if statements already, right? You have an if statement, and then it has a colon at the end so that there's a block of code underneath it that is indented. That's just part of the syntax. And the fact that that word is if is part of the syntax. If somebody in France had made up this language and felt like not making it English in order to hit the broadest audience possible, they could have chosen, the French word for if, whatever that is. I keep using French when I've never taken a French course. I should use Spanish, but I've forgotten all my Spanish too. High school was a long time ago. So the mistakes in the language are called syntax errors. So what is the computer memory? Essentially, there are two kinds of memory. One kind of memory is the kind that gets lost when you turn your computer off. That's why it has to reboot when you turn it back on. That's called random access memory. Why is it called random access? Because it can read any particular address in it. The chip can go and say, I want the data. Give me 4 bytes starting at address 2 big and 3. Right? So it'll go and get that. It's randomly accessing it. Well, what other kind of access could there? Well, what if it had to start from the very beginning and go to the very end? Well, that's like punch cards, right? You give it a stack of punch cards and it's got to load them into a reader, and if it wanted, punch card 17, it's got to go flip, 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 flip until it hits 17. Or a tape drive, right? It's just got to start at the beginning and then it's got to scroll to the end. So, fortunately, we don't have to use that kind of stuff. So that's known as volatile memory, not volatile like I'm going to explode, but because it's lost when the power's turned off. Volatile just means very changeable. If you have a volatile liquid, whatever, some chemistry definition of it that I can't recall. And non-volatile means permanent. Well, not permanent in as once that it's set, it never changes. That'd be really permanent, right? But that'd be kind of useless too. It just means that it maintains its state when the power is off, right? So you can eject that SD card and bring it over to another camera and load it up and put it on your phone or whatever. And you can still see the pictures even though there wasn't any electricity. Or your hard drive, right? You power down your computer and the hard drive, you know, maintains its information, otherwise it'd be useful. Useless, not useful. Then you have something called the compiler, which takes that source code that you write, these if statements and x equals 3s and stuff like that, and turns it in to some kind of machine language that will run on the computer. Because machine language is just a series of zeros and ones that make up the numeric commands that drive the chip. Right? One command would tell the chip to go and pull data from a specific address. Another command, these are called opcodes, operation codes, would tell the chip that you wanted to add that number to something else. And then a third opcode would tell it, okay, copy that information to a different address. So it's just a series of numeric commands that drive that chip. But something has to turn our English program, if x equals 3, print y, right, into those series of opcodes. And we're not going to get into the techie details, but that's done by compilers and interpreters. So when we run our program, we use the word run. Fancy word is execute. Sounds scary. And we're going to execute our program. No, don't do that. Yeah, it just runs the program. That's why they're called .exe files. They're executable files. So a program with a syntax error cannot execute. You can have logical errors. Logical errors if it just produces the wrong output. Say I have a programmable thermostat in my phone, in my home, and it turns on the air conditioner every time it gets below 40 degrees, right? Well, I don't want it to turn the AC on when it gets too cold. I want it to turn the AC when it gets too hot. That means that the program is written wrong, so that the if statement is, whatever. So it gives you the wrong output, but it's not because there was a mistake in the syntax, right? There weren't colons in the wrong place. Instead, the instructions, the program we gave it, made it do the wrong thing. So that's the difference between a syntax error and a logical error. One textbook that I use called that a semantic error. Semantic error is when it gives you the wrong output. Well, I like the term logical error a lot better, so I'm thankful for this textbook now. So the logic of the computer program is a sequence of the instructions. Input x, x equals x times x, print x. Right? Those three statements are the logic. So what's a variable? It's a named place in memory, right? A named place that can hold a value. Well, why would you want that? Well, back in olden days, before nice programming languages like this, the programmer would just pick a memory address in which they wanted to store the data. So they wouldn't say x equals 3. They would say write 3 out to location 1000, and then write 4 out to location 2000, and then add location 1000 and 2000 and write that result out to location 3000. Right? You can see why that would be a real drag if you had to pick these numbers out of your hat. So fortunately, around the time of the 50s, people came up with the idea of writing programs in a syntax that could be compiled into that machine language, and when that program ran, that program could pick 1000, 2000, 3000. And we didn't need to do that. Well, not that I was there, right? Because when we ran the program, it would say, okay, I need X, and then the computer would go, okay, you got a place named X, but behind the scenes, it's really location 1000. And you say, okay, I need another place to store a different piece of data, Y, right? And it would go, okay, Y is secretly behind the scenes 2000. So every time you refer, it's just like giving nicknames to addresses, right? I don't want to have to tell you that I live in 123 South Main. I would just like to be able to tell you that maybe one time, and then from there on out, say my house, right? Because I don't want to have to repeat that over and over and over every time I'm talking about my home. So it's just a Synonym, a nickname for an address. So it's got a name, but its value can vary. It's why it's called a variable. So programming development cycle. You got to understand the problem. Like if you were going to get paid for this, you'd ask a customer to describe the problem. You'd help them write up specs, or you'd write up the specs. And if you're smart, you'll run the specs by the customer before you've spent a lot of time writing the program. You got to plan the logic. Okay, how's this going to work? Based on that logic, you code it. And then you run it, you test it. This is pretty simplified. But the problem is that if you test it and there's a mistake in it, it might be because you just made a syntax error. It might be because you made a logic error and you need to go back and think about replanning the logic. But the worst problem is when the customer says, no, here's what I really wanted it to do. And so hopefully you can bill them more for the extra 100 hours you're going to have to do to implement their new requirements. It's a very, very common thing. That's why you want to work real hard to nail down your specifications if you're dealing with somebody else, because catching a mistake here is a lot cheaper than catching that mistake when you get all the way down to here. You show them the result and then they say, no, I really wanted to do it again. And so you have to go back to square one and start replanning the logic. So maintenance is just fixing the bugs in it. Right. I send my thermostat program to some programmer and he fixes the mistake that was causing it to switch on when the weather got too cold. Right. Very common job for, beginning programmers is maintenance on a larger system. Right. You don't write the brand new stuff yet. You got to learn how to fix the old one, and in that way you pick up on how everything works there. Or adding new features can be part of maintaining too, right? Somebody wants a new report, right? Or a different report. We want to be able to sort the data by last names, and so then they would go and add that, not just making little bug fixes. So there are hundreds of programming languages available. Some of them even have obscene names, which I'm not going to mention. Those are the programs that are kind of written for fun and written to be deliberately difficult to write, kind of like logic puzzles. So you write your program. You click the run button. It compiles the program. If syntax is bad, it prints out a list and you got to fix your program again. If there are no syntaxes, you have an exe. Well, we don't really have an exe, but the program starts running. The machine language starts running. And if it needs data, it gets some data, and then it produces the output. Testing the program. Programmers test to see if their program works, right? I want a program that's going to add 2 numbers. So I test it. It adds 2 numbers. Rock and roll, I got it working, right? Hands done. Nah, if you're going to give it to a customer, you don't only want to make sure that it works, you want to make sure that it can't fail. Those are 2 different things, right? So you got to make sure that if they type in a negative number, it still adds those 2 numbers together. Or if they type in, garbage, that it doesn't crash the program, or whatever, right? Or that if they type the wrong thing, that it writes, something out to some memory location that shouldn't and corrupts things later. Right, there's all sorts of things that can go wrong in a complex program. So running it once and seeing that it works isn't really good enough in a professional environment. So that's testing. Usually the programmer tests their program and they try to get it real good. And then if you're working in a large team, you might pass that on to a testing department. Because just like if you're writing your own English paper or whatever, you may not be able to pick up the mistakes in the syntax. I mean, typos and stuff like that, because your brain just knows what you meant. That's why when I'm walking around and y'all are getting compilation errors, I can usually look at it within 5 seconds and spot it and fix it. Whereas you could stare at it for a long time until you get more experienced at it, and then even then it can be a little bit of a problem because you know what you wrote, right? So your eyes are seeing what your brain thinks they should see. And when I walk over there, I don't have that preconception, so usually it can jump right out at me. So that's a test. You ought to test your program to see if you can break it. Now, in our early stages, we're not going to do that, right? Because that makes programs much longer. Quite often, a program will have just as much code dedicated to error handling as to running correctly. So debugging is the process of finding those errors. Okay, so it crashed when I entered 0, right? So I got to figure it out. I got to run it. Maybe I have to add some print statements. If the language has something known as a debugger, maybe I could step through it line by line and watch the data change. So that's debugging, finding the bugs, right? So the first computer bug. Lady named Grace Hopper, who invented programming languages in the 50s. Essentially, she was the creator of the idea of programming languages rather than machine language. But she was supervising a project. It wasn't working. And back then, 40s and 50s, computers didn't have solid state chips in them, right? They had vacuum tubes and relays that would click and stuff like that. And so they finally traced it down to a relay with a bug stuck in it, right? Well, there's your computer bug. But apparently the term dates back even further than that. You know, like Edison might have referred to, you know, a bug in his systems or whatever. But, you know, a bug is just something that doesn't, that's giving you, it's a logic error. A bug isn't a syntax error, it's a logic error. So debugging is the act of searching for those bugs and correcting them in your program. Pseudocode and flowchart. What is pseudocode? Pseudocode is an English-like representation of the logical steps. But it's not a programming language. I could give you pseudocode, and if you knew C++, you could write a C++ program. If I gave it to a Java programmer, you could write that program in Java. Have we done this yet where I say, okay, this is the logic for a payroll program, something like that? Have I done pseudocode like that? Okay, so say I just wanted to plan out the logic for a program that, didn't I have Notepad already open? Maybe not. That could calculate pay and overtime based on time and a half over 40 hours. Alrighty. Well, according to the book, this is what my pseudocode would look like. Let me see if I can make this a little bit larger. They want pseudocode to always start with the word start. So I'll abide by that. Input hours. I'm not telling the person how to write the code that would input the hours because every language does it differently. Input hourly wage or hourly rate, and then set the total equal to hours times hourly rate, right? So if I work 10 hours and I earn $10 an hour, then that's $100. But now we got a problem. We have to handle that overtime. Overtime only happens if the hours are over 40. That's kind of conditional, right? You don't get overtime bonuses if you didn't work more than 40 hours. Does anybody earn overtime anymore? Is that still a thing, or have they found a way to just not pay it? I know if you're a salaried employee, I certainly don't get paid for, you know, staying late, but I think that
they're trying to do away with it in lieu of vacation time that you won't be able to actually redeem very well, but it's currently in the progress of going through Congress.
Oh, great. All right. Anyways, okay, so if our hours are greater than 40, and I didn't put a colon there because this isn't Python and another language wouldn't want a colon, and I don't want to clutter this up with too much syntax that looks like a specific language, although I can't help it. Since I know Python and Java and C++ and a bunch of languages, I kind of make my pseudocode look like those languages to some degree. But I'm trying to teach the book rather than doing my own personal thing. So, okay, so if hours is greater than 40, we're going to set the bonus equal to, and I'm going to give you an equation, and I've had students argue about this equation because there's more than one to calculate time and a half. This is the way that makes sense to me, so I'm going to give you this equation, but it's not the only one. So hours minus 40, right? So if you work 50 hours, you get 10 hours of overtime, times the hourly rate divided by 2. That is the equation, an equation for calculating it. And then set total equal to total plus the bonus pay. And you don't have to type this into idle because it's not a program, right? But you could. If I had typed it into idle itself, if I had launched idle, and I wanted all that to be there, which I probably really do, honestly, so that it'll be in the notes. I think we're on Lecture C, so save as Lecture C. Please don't start typing things directly into the shell. Thankfully, y'all aren't doing that, but in another one of my classes, people are still at the point where they're forgetting to do file new at the beginning of it. So what is this? This is Lecture C. We're still in Chapter 1. This is Jan 29. This is CIT1113 All right. And I'm just going to go and copy and paste out a notepad. And you don't have to do all this. But anyways, I'm going to start off my comments, my big set of comments, with triple quotes. You can use double quotes or single quotes. I know I've said that before. In between those two pairs of triple quotes, I'm going to copy my stuff out of here. All right. And why not give it a description? Pseudocode for calculating pay with overtime greater than 40. Good enough, right? We understand what that means. So we've done a bunch of calculations here, but we haven't output it, so I'm going to output the total. So that's my pseudocode for calculating overtime pay. I could turn that into a program. Might be a cool idea to turn that into a program. I think we'll do that. That'll be like one of the last things we do in class today. Well, not one of the last, right? We had like 30 minutes left. But that's the pseudocode for it. A couple things to notice about it. There's some kind of keywords, input, and set, and if. And in pseudocode, and I'm sorry that this is different than Python, and we're not going to talk about pseudocode through the whole thing, but there's differences in syntax. Because if this was Python, I would put a colon there. If this is Python, I wouldn't have the word set. If this is Python, I would not have the word end if, but it's just because it's two different languages. Pseudocode is a generic language that's used to specify logic. It's not a specific computer language. Kind of like learning Latin and English, different rules. So we're going to do a few things where I may ask you to write pseudocode, but for the most part, we're going to actually write programming code, right? We're going to write Python because it's more fun to type something in and actually see it work. All right, that would do it. That would do it. So our rules are that if you have some indented code, it means that that code only happens if this is true. When you stop indenting, there needs to be a word that tells you what was coming up or what had already happened. Right, and so this code was part of an if statement, and so this marks the end of this if statement. Well, why do I have to have that? I could just look up 2 lines and see that it's right, but no. What if this is 2 pages of code, right? Then when you stopped indenting, you'd like to know what was going on. You might even want to put a comment here. If you were writing real code, right, you know, end if hours greater than 40. I'm not going to do that. I'm not going to add comments to my pseudocode, but I could. All right, so it's just a description of an algorithm. An algorithm is a series of steps. Algorithm is a series of steps to solve a problem, whatever that problem is, even if it's just to amuse yourself, right? It amuses me to calculate the value of pi. No, not really. And then pseudocode is an English description of the algorithm, kind of in a specific format. But it doesn't have to be precise or anything like that. I could say, ask user, don't type this, for hours, store in hours variable, right? I could do something like that. Or I could say output how many hours. Don't do this either because I'm going to erase it. And then input hours, right? That would still be valid pseudocode. Or I could say, you know, whatever, right? I could change it into various things and it would still work because it doesn't have to be precise. It's not a specific syntax. They're just some words that we'd like to remember. They use the word set to indicate that a variable is being set. Great. You'll see some textbooks that like to put like an arrow there. That seems kind of superfluous to me, but, right? But since it's loosey-goosey, the syntax can vary. As long as it's kind of consistent while you're looking at it and it makes sense. Meanwhile, a flowchart is a picture representation of the logical steps it takes to solve the problem. I think I'll draw a flowchart for this really quickly. I'm not going to ask you all to copy along with me because I want to get to actually programming it. But I'm going to use a site called Lucidchart, and you'll probably wind up using it too. It's not remembering my password. That's a drag. I'm not going to do the flowchart. I'm just going to show you a picture. I'm assuming they have a picture. Maybe I'll draw it on the board. That's what I'll do. Sorry, guys, who are watching this at home, but I'm drawing this on the board. So where's my pseudocode? I guess I can take a picture of it, right, and paste it into the notes. That's the notepad. Don't want that. Want the one I typed into here. All right. First thing is start. Okay. Start. Flowcharting wants an oval at the top and an oval at the bottom. The top of it says start, and the end of it says stop. So I'm going to have another oval at the bottom. And then input hours. Now input statements go in a special shape. They go in a parallelogram, a tilted rectangle. Yeah, like that. Like that. Oh, really? Here we go. Oval start and stop. That's why we had that. The next statement was an input. And so it goes in that shape. This one has a symbol we don't use. Display. So input hours. I'm just going to write that in here. Input hours. The third shape was an input hourly rate. So I need another tilted rectangle. Input hourly rate. Forgive me for not writing the whole thing. Set total. Well, sets are calculations. Math statements go in rectangles. This little description called them a process block. So I would put my algebra in that process block. So hours, I'm going to leave off the word hours as set though. Hours equals, total equals hours times hourly pay, right? Then we have an if statement. We've got logic. Oh, please tell me I didn't write on it. All right. So we have a logic. That looks like that. Decision making. It's a diamond. So I'd have an if statement. If hours greater than 40, and the book's going to show you not putting the word if in the block. I like putting the if in the diamond because the diamond is used for multiple things. The diamond is used for while loops and for loops and stuff as well as if. All right. I'm running out of room, so I'm going to simplify this. I'm just going to pretend that we calculated the blah, blah, blah. We had a series of process steps, right? We had two different set statements, set. And then it comes back and it joins together at that end if, right? And then we output the total, right? Output total. And then lastly it stops, right? So there's a stop at the bottom. You know that sign that says plan ahead, and plan is written in great big letters and ahead gets smaller and smaller. So anyways, okay. and everything has to be connected. We should be putting little arrows to show the direction. Did I have to make it so that it goes down? Could I have made it go to the left and start going off to the right? Nah, as long as you have the arrows right. This is standard. It makes it easy to read. But if I had run out of space here, which I honestly did, I would just draw an arrow going back to the top of the next column, right? Okay. So you see that our indented code here is represented by shooting off to the side. This is all my indented code. And then once they join back together at the end if, then we have these final steps. The output, the total, and then the stop. So that's a flow chart. I'll draw that rather than take a picture because that's a pretty miserable looking drawing. All right, let's turn this into a program. Let's actually turn this into Python. So what are we going to do? Well, just eyeballing it, Python doesn't use start and stop. So I'm sorry about that. It's not going to have start and stop. It is going to have an input statement, but the syntax is different. The syntax for an input statement is something more like this. Whoopsie, Y caps. Hours equals, then input, how many hours, right? Something like that. Okay, I'm going to flip over and actually start coding that. So I'm going to end my comment because here's where our code is going to begin. Code for pay calculator. That's just my comment. Based on above pseudocode. Now the book will show having a block where you define all your variables in advance. I could do that. I could say hours equals 0, hit enter. Hourly rate equals 0, hit enter. Bonus equals 0, hit enter. Total equals, right? I could define all my variables in advance. I'm gonna make this match as closely as I can to this. So hours equals input. You don't have to put those spaces. Parentheses in parentheses, and inside the parentheses, I'm going to put what I want them to type in, because otherwise they won't know. How many hours worked this week? Question mark, end quote. And it colorizes it to make it easy to spot, right? If this parentheses was green, I would know that I messed up the syntax. I'll also know when I run it, and it tells me it's a syntax error. We may experiment with using PyCharm. I'd like to do that because it's got some cool functionality where if you start to type a word in, it offers to fill it in, right? And it catches mistakes, like if you make some variable uppercase and then you try to use it again lowercase even before you run it. I think it'd be cool. Okay, so the next line, input hourly rate. Same business. The variable name, hourly underscore rate. And yes, I could have chosen like single letter variable names. I could have said x equals input this and y equals input that. But it's a real good idea to make your variable names descriptive. Now you'll see me use x and y and stuff like that just because they're easier for y'all to type. But in this case, I wanted to go full tilt and make it look like a good program. Right, because you might make a mistake in typing hourly. You might leave off the R or whatever, So sometimes I use single letter variable names, but the rule of thumb is to not do so. That you ought to use good words for your variable names. All right, so hourly rate equals input, parentheses in parentheses. Inside the parentheses, I'm going to put 2 double quotes, and inside the 2 double quotes, what is your hourly pay rate? Question mark. Now I'm going to be all fancy and stuff. So after the question mark, before the quote, I'm going to put 2 spaces, 2 minus signs, and a greater than sign. Same thing down here. 2 spaces, 2. This is not important. I'm just doing it to make it look good. Let me show you what it'll look like and why I like it, but you don't have to do it. Right? There. I like that, right? Because sometimes when you use an input statement, it'll put it, on the next line rather than putting it here. And so I'd like to show them where to type it, make it real blatantly easy to see. All right, now set total equals hours times hourly rate. I'm going to put some comments here above my quotes. Turning pseudocode into Python. There's no start or stop word. Oh, I deleted them. Start and stop. That was not my intention. There's no start or stop word. There's no set word. Or if there is, it means something completely different. So when I type set total equals hours times hourly rate, honestly, I may slip into the habit of leaving the set word off entirely. And if you do that, I'm not going to count you off. So, next line, total equals hours times hourly rate. I could just copy and paste it. Total equals hours, asterisk, hourly underscore rate. Now we have our if statement. It's the same logic, just with a colon after it. So again, I could copy and paste it. If hours greater than sign 40 colon, and again, I'm putting all sorts of spaces where I don't have to. I could delete almost every space I've typed up here except that one. Why couldn't I delete that space? Because it makes it, a new word. So if hours greater than 40, the next line is going to be indented. Then bonus equals that equation. Hours minus 40 in parentheses. So open parentheses, hours minus 40, close parentheses. Asterisk times hourly. That's such a childish word. We should use multiplied by, but it's so easy to say, times hourly underscore rate / the one under the question mark 2. Why did I specify under the question mark? Because there's also the backslash. I don't think this language uses a backslash, thankfully. Other languages do. Yeah, it does, for \n, printing a new line. Anyways, and then the next line was set total equals total plus bonus. Total equals total plus bonus. There's no such thing as an end if. I'm going to go back and add that to my little comments about turning pseudocode into Python. There's no end if. But you can add as a comment if and you once. So I'm going to come down here and add it as a comment just to make it look almost one for one. Alrighty, then you can, so make sure you're back tabbed at that point because the next code needs to be back tabbed, right? Because we're done with our if block, and so we're going to output the total. So instead, our rules for turning pseudocode into Python, there's no print word, there's no output word, instead it's print. So print, come on, I keep backspacing. Print, parentheses, quote, total pay equals, or is, the word is, end quote, comma, or I could have said this week's pay, right? End quote, comma, total, in parentheses. And we're done. If I wanted to see the word start, I could add it as a comment up here. I could put hash start, and I could put hash stop here at the bottom. My program's done. Maybe. I haven't run it. So I'm going to run it and see if it works. Then I'll walk around and see if y'all have syntax errors you want help. All right, how many hours did I work? Okay, I'm going to work 40 hours at 10 hours a week, and that should give me 400 if my calculation's right. 40 at 10. Kaboom! I forgot something. Somebody remember our previous programs? Did we convert from a string to a number? Do you remember how we did that? I had to turn these into floating point numbers in order to do math on that. So after I get my input, I need to turn it into a float. So hours equals float, parentheses, hours in parentheses. I better add that to my notes. after input, you may or might use float to convert it to a number. Because whatever's typed in is a so-called string, which is just a series of characters from the keyboard. Now, the language doesn't know that from Adam, right? Because I could have typed in the word Adam, and then it wouldn't be able to do math, right? So that statement would crash if we typed in something that with letters in it rather than a number. I need to do the same thing for the hourly rate. So underneath that line that says hourly rate, you know what? I may start adding a white space to make my code easier to read. I may start adding some returns. Okay, so underneath hourly rate is equal to input, I'm going to do hourly underscore rate equals float, parentheses in parentheses, and inside those parentheses, hourly underscore rate. By the way, I did not make that mistake intentionally. Sometimes I do, so that we have to go back and fix it. But the more we have to go back and fix things, the more people get lost. So I try to kind of minimize that. Give it a go. All right, how many hours worked this week? 40, $10 an hour, 400. Okay, cool. I'm going to run it again, and I'm going to work 50 hours this week. 50 hours this week at 10. That means I work 10 hours of overtime, so I should get $50 extra of pay if my brain's working right. So 550. All right, got it going. Let me pause it and come help y'all, and then I'm going to give you a pseudocode for a program that I want you to write. That's not the pause button. Let's go look at the homework assignment. All right, write a program that performs the following tasks. Ask the user to input a value in, do these calculations, and print the results. And so, by the way, asterisk asterisk means exponent, which means to the power of. And slash slash means floor division, which means divide and round down. So if you have 5 divided by 2, it's 2.5. But if you put 5 slash slash 2, it's going to get 2.5, but round it down to 2. All right, so let's write some pseudocode for this. Now, you could write it in your own way if and you wanted. Don't have to do it the way that I'm about to do it. Pseudocode for homework. Start. Input. We just need some kind of number. What did I say that number was supposed to be in? And I don't know why I made it a capital letter N, but I'm going to do that. All right, and then it's going to do some math. It needs to calculate this and display the results. All right, so how about R for result? Set R equal N times 2, and we're going to print our results. Output N times 2 equals end quote comma R, right? And then I'm going to do the same thing to the exponent and the divide and the floor division. So I'm going to cheat. I'm just going to copy those two statements, paste, and make the changes required. So the first time it's an asterisk, the second time it's 2 asterisks, which means exponent. I may even put a comment to that effect. The third set, I'm putting spaces to make them easy to read right now, but I might delete them in a minute. I'll leave these in the notes though, of course. The next one is division. We know what division means. And the last pair of statements is floor division. So slash slash means floor division means round down. And that's the end of the program. If you want to go from the pseudocode, that's fine. If you want to write it in a different way, that's also fine, because I'm not copying and pasting this into the homework. It's just going to be in the notes. I'm going to end my comment with more triple quotes, or else it might not compile and run, and I'm trying to keep this program a working program. Right, all right, seems to be working. If I run it again, I'll bring that code back up, don't worry. If I run it again, and I type in garbage like that, it fails, tells me line 49. I can come back to my code. I can put my cursor anywhere, and then I could use this little line counter here at the bottom to tell me where it failed. And it failed in line 49, which was converting that garbage that I typed in into a number. So it turns out not to be a syntax error. It's because I gave it the wrong input. All right, gang. I'm going to go ahead and create the drop box for those who are fast typists or aren't typing in anything, and then I'll toggle back to this page, okay? So just a sec.